Black holes evoke a mix of awe and primordial fear. They're among the oldest objects in the universe, and no one has ever escaped their deadly grasp to reveal what lurks in their dark depths. Today, we delve into the secrets of black hole formation and explore why these anomalies exist in the vast cosmos. Black holes are objects that can't be observed directly, like asteroids, planets, or stars, but their existence is virtually unquestioned, backed by hundreds of indirect studies and astrophysical calculations. Essentially, a black hole is a funnel formed by matter so dense that it sinks into space-time, warping it profoundly. The result is an invisible monster whose presence is detected through its interactions with nearby bodies. For instance, if a star or nebula is close enough, the black hole gradually devours the victim's matter until it's completely gone, swallowed into the insatiable abyss. The swirling accretion disk near the event horizon, the point of no return, allows us to identify these cosmic predators. This disk is a glowing ring of superheated gas and plasma, accelerated to near-light speeds as it spirals inward, emitting X-rays and other radiation that telescopes can detect from billions of light years away. There are four main hypotheses explaining how black holes form. The first suggests that a massive body, at least 3 times the sun's mass, collapses so violently that it instantly becomes a black hole. This collapse happens for physical reasons. When a star's nuclear fuel runs out, the outward pressure ceases and gravity crushes it inward. If unopposed, this leads to a black hole plunging into a space-time funnel. Consider a massive star like Betelgeuse. If it goes supernova, its core could compress into a stellar mass black hole in seconds, leaving behind a remnant that's invisible but gravitationally dominant. The second theory posits that gas clouds and galactic centers can compress enough to birth these invisible giants, forming supermassive black holes that anchor galaxies like our Milky Way's Sagittarius A star. The other two are more hypothetical due to their low probability. Some astrophysicists propose primordial black holes form from nothing right after the Big Bang. Tiny seeds that could explain dark matter if they exist in vast numbers. The last scenario involves micro black holes created in particle accelerators like the Large Hadron Collider or high-energy nuclear reactions, though none have been detected yet, raising questions about quantum-scale gravity. Regardless of origin, anything crossing the event horizon leaves our world forever. To understand what's inside, scientists use conditional classifications. The first type, calculated by Carl Schwarzschild in 1916 during World War I, assumes a singularity at the core, a point of infinite density where physics breaks down. Schwarzschild's solution to Einstein's general relativity equations described a non-rotating, uncharged black hole, revolutionizing our view of gravity. The second, by Hans Reisner in 1916 and Gunnar Nordstrom in 1918, adds an electric charge to the singularity, creating electromagnetic effects that could influence nearby particles. The third, from Roy Kerr in 1963, describes rotating but non-charged black holes, which are more realistic since most stars spin and conserve angular momentum during collapse. In 1965, with Ezra Newman, Kerr added charge to this rotating model, creating the fourth type, the Kerr-Newman black hole, which combines spin, charge, and mass in a complete metric. For the simplest Schwarzschild black hole, the structure includes an outer event horizon and the singularity, a bizarre state of matter approaching infinity, defying known laws. The event horizon is the boundary where escape velocity equals the speed of light, about 2.95 kilometers for a solar mass black hole. In other types, this is supplemented by an ergosphere, a region outside the horizon where space-time drags along with the black hole's rotation, potentially extracting energy via the Penrose process. There's also a slight electric impulse in charged models, which could lead to exotic phenomena like charged particle jets. Stripping away theories, a black hole's interior might simply contain what it has consumed: neutrons from the colossal compression during formation, crushed into a soup of quarks or even more fundamental particles under extreme gravity. What about mass, density, and temperature? A black hole's mass derives from its progenitor. The heaviest observed, like TON 618, weighs around 66 billion solar masses, but recent detections push boundaries further. For example, stellar mass black holes range from 3 to 100 solar masses, while supermassive ones in galactic cores can exceed billions. Density is mind-boggling. Smaller mass means higher density, with quantum black holes reaching 10 to the power of 94 kg, compared to water's 1,000 kilograms per cubic meter or a neutron star's 10 to the power of 17 kg. This inverse relationship arises because the Schwarzschild radius scales linearly with mass, so volume, proportional to radius cubed, decreases faster for lighter black holes. Black holes are frigid, often around minus 270 degrees Celsius, near absolute zero, as predicted by Hawking radiation, where virtual particles at the horizon become real, causing slow evaporation over eons. Though theoretical hot ones, microscopic black holes, could emit energy like millions of atomic bombs exploding simultaneously, releasing gamma rays in a final burst, none have been observed, and their existence remains speculative. Why do black holes exist? Nature's purpose remains elusive, leading to speculative ideas. One realistic theory views them as generators of alternate universes, where singularities might be controllable from another side, perhaps birthing baby universes in a multiverse framework proposed by cosmologists like Alan Guth. Another sees them as regulators, preventing gas clouds from cooling and thus controlling star formation rates in galaxies, maintaining cosmic balance. Some astrophysicists believe black holes are efficient energy producers, converting atoms to subatomic particles 50 times better than nuclear fusion through processes like accretion and jet emissions, powering quasars that outshine entire galaxies. Others call them God's hand, creating substances essential for the universe, recycling matter and energy on a grand scale. More exotic theories compare black holes to portals or living organisms governed by programmed matrices, allowing selective passage, like a cosmic nightclub bouncer deciding what enters. These ideas stretch into realms where black holes might connect dimensions, as in wormhole theories by Kip Thorne, or harbor advanced civilizations using them for time travel or energy harvesting. Some even suggest black holes are holographic projections, with all information encoded on the event horizon, challenging our 3D perception of reality. Recent discoveries in 2025 have revolutionized our understanding, thanks to advanced telescopes and gravitational wave detectors. NASA's James Webb Space Telescope, JWST, has spotted possible direct collapse black holes from the early universe, like one in the Infinity Galaxy from the Infinity series, hinting at formation without stars through massive gas clouds collapsing directly. In August 2025, astronomers announced the universe's oldest known black hole in a little red dot galaxy, part of the Kuiper's LRDZ-K9 system, present just 500 million years after the Big Bang, 13.3 billion years ago, adding evidence that supermassive black holes fueled early galactic brightness and growth. Dual black holes devouring a galaxy were observed in May 2025 by UC Berkeley astronomers in a stealth companion to a core black hole, potentially leading to a merger. The most massive merger detected by gravitational waves in July 2025 via LIGO Virgo created a 225 solar mass giant, with the resulting black holes spinning at high rates, providing insights into binary black hole dynamics. Theoretical breakthroughs include a March 2025 study in unimodular gravity suggesting black holes transition to white holes, ejecting matter via quantum effects, and resolving singularities without violating unitarity, meaning information isn't lost but recycled. This could imply black holes aren't endings, but beginnings, potentially recycling the universe in cycles. In June 2025, the Subaru telescope team discovered a tightly packed cluster of supermassive black holes 10.8 billion years old, challenging models of early universe formation. JWST also observed star-shredding black holes in dusty galaxies in July 2025, capturing tidal disruption events where stars are torn apart, revealing hidden intermediate mass black holes. Black holes also test quantum gravity. String theory proposes no singularities. Instead, fuzzballs of tangled strings resolve infinities, while loop quantum gravity envisions Planck-scale quantum foam bouncing back from collapse, avoiding true singularities. Hawking radiation, predicted in 1974, suggests evaporation, but 2025 simulations using quantum computing confirm information might be preserved holographically on the horizon, solving the black hole information paradox through entanglement and firewalls. Observations like the Event Horizon Telescope's 2019 image of M87's black hole, updated in 2025 with polarized light showing twisted magnetic fields, reveal accretion dynamics and jet formation. Sagittarius A*, our galaxy's supermassive black hole, showed rapid flares in JWST data from April 2025, indicating turbulent inner processes and possible mini-jets. Hubble and Chandra spotted a rare intermediate mass black hole eating a star in July 2025, bridging stellar and supermassive classes. Future missions, like the Laser Interferometer Space Antenna, LISA, launching in the 2030s, will detect more mergers, probing primordial black holes as dark matter candidates. Theories speculate our universe resides inside a black hole, with a Big Bang as a white hole rebound, supported by 2025 JWST data on galactic rotations, suggesting cosmic spin inheritance from a parent black hole's rotation. A Yale-led team in July 2025 found evidence of a newborn supermassive black hole in a galaxy from the cosmic dawn, directly after formation, adding to the infinity from the infinity dataset. Black holes remain shrouded in mystery, but we've glimpsed their secrets through these advancements. We hope this exploration sparked your curiosity. Stay tuned for more cosmic adventures and subscribe for the next chapter.